And you get your quizzes back a little bit later today. There's just a couple of people that wrote at lunch, and I need to mark them. I just want to get them marked and out of the way before I return them to you. Just a reminder to everybody, remember, please, that when you're absent, you're responsible to look at Google Classroom and see what it is we did, and you're responsible for the material that was missed and any instructions there. If you did not show up for the quiz today at lunch, then I need you to show up. Well, I would prefer if you write it after school today, the couple of you that still have to write it. But if that's not a possibility, and I know that with at least one person it's not, then tomorrow at lunch, near the beginning of lunch, come in here and write it and get it out of the way. It was about 10 minutes. It didn't take you that long. But I will get those back to you a little bit later today. In the meantime, what we did on Thursday was we were solving trigonometric equations. So it doesn't matter whether you're looking in your textbook at question 7 or 8 or 9 or 13, or whether you go to the additional problems on page 25 of your handout, they all boil down to the same thing. In all of these questions, you were told the value of a trigonometric ratio. For example, let's take number 7 and just remind ourselves how you find the angles. The key to answering this problem is to recognize that we're talking about any rotation angle from 0 degrees to 360 degrees. So the first thing you do, once you know that sine of theta has a value of 5 over 13, this is the trigonometric ratio. It's the ratio of y over r, but that's really not that important in answering this question. Your first step is to unwrap the sine and find a reference angle by taking the inverse sine of 5 over 13. And I know there were a number of you that were absent on Friday. I hope you watched the video, but it's really, really important that you understand when you go inverse sine on your calculator at this level, you're not finding the angle, you're finding the reference angle. Okay? So this angle that we're after, right here, this, which is what we want, is not what my calculator is going to spit out necessarily. Okay? So I take the inverse sine, making sure I'm in degree mode, and I am. I take the inverse sine of 5 over 13, and I get that. And by the way, some of you prefer, I know, to take 5 divided by 13 and then take the inverse sine of it. It doesn't matter. I don't think you really need to. I think you can just do it in one shot. So then you would go inverse sine of that number. Anyway, the reference angle is 23 degrees, and I'm going to use 23 degrees because it does say to the nearest degree. So my reference angle, sure, it said 22.6. Yep, so 23 degrees. This is one of the preliminary steps in finding the rotation angle, which is theta, which I have underlined with those 3 red lines. What you need to do now is answer this question. Which 2 quadrants? And you answer that based on knowing that this ratio is y over r, and in the question it said that sine was positive. So what does that mean? It means this rotation angle, not the 23 degrees necessarily, but the rotation angle has to be in a quadrant where y is positive. Well, that's these 2 quadrants up here, quadrant 1 and quadrant 2. So you find the reference angle, you answer this question, and then you sketch the 2 possible cases. So if the rotation angle lies in quadrant 1, and the reference angle is 23 degrees, then what is the rotation angle? That 23 degrees is not the rotation angle, that's the reference angle. On the other hand, if The terminal arm lies in quadrant 2, another place where y is positive, and the reference angle is 23 degrees. Then what is the rotation angle? And then once you find those out, you're done. I know this should be very basic, but it's been a few days. If you have a terminal arm in quadrant 1, whatever the reference angle is the rotation angle. That's, you can see they're identical. And again, I've said this so many times, but the reference angle has no direction. It's just an arc, whereas the rotation angle has a direction. Anyway, I get theta equals 23 degrees. And over here, I would have to use what I learned, man, I want to say the first day of this unit, that we would have to take 180 degrees and subtract the 23. Back off the 23 and get 100 and, well, I'll write it down so I can see the numbers. 180 minus the 23 is 157. Seeing some nods. So the other rotation angle would be 157 degrees. So they all boil down to that. Now, some of you might, if you take a look at number 12, you might go, well, 12 doesn't tell me a trigonometric ratio that I can inverse. But since I know y and since I know y and x, why don't I just use tangent? Tangent is y over x, and y is 4 and x is -9, so there's my trigonometric ratio that I can use. Now I'm going to do this example with you to remind you of what we did, plus there were 9 people who were away on Friday. So there's a lot of people who, and I really hope you watched the video, but if you didn't, this is important. You don't have to convert that to a decimal. What we have is tangent of theta, I'm going to rewrite it, is -4/9. And I'm putting the negative where I hate negatives. I hate a negative just out in front. I'd rather have it on the top or the bottom, but that's okay. Because the point I want to make, and I think I would have made this point at least 8 times in the lesson, maybe not, is that you would take the inverse tangent of 4/9. You would not include the negative when you take the inverse. Okay? So that's really important. If you start including the negative, you'll get some weird answers, and you might be able to figure it all out that way, but it's confusing. I will tell you right now that if you use the negative when it's there, you'll have to learn one set of rules to follow for sine, a different set of rules to follow for cosine, and a third set of rules to follow for tangent. It's confusing. So what you would do here is take the inverse tan of 4/9 to get a reference angle of, I'll say 24 degrees to the nearest degree. You would then look at the reality of it, which is that this is negative. You didn't use the negative when you found the reference angle, but now you need to look at it. And you need to say, since tangent is y over x, which quadrant is it in? Now this is tricky because I was about to say, what 2 quadrants could it be in? It's only in 1 quadrant though, right? Because it tells you the point is -9, 4. Is that what it says for this question? -9, 4. So you know it's over here. Whoops. You know it's over here where x is negative and y is positive. So in this case, you draw that reference angle of 24 degrees. And you find the rotation angle, which is what I'm indicating using the black pen this time. And you would take 180 minus 24. Okay. Does anybody have any specific questions you would like me to go over from, let's start with the textbook. So that would be anything from questions 7, 9, 12, or 13. What about the additional problems on page 25 of your handout? I think it was 8, 9, 10. Yeah. Any questions from any of those? All right, so we are going to be moving on here. We are done with the part of the unit dealing with coordinate trigonometry, and now we're going to land into more comfortable space that you're more familiar with, which is just working with triangles. And today and tomorrow we're going to be looking at something called the sine law. And on Thursday, we're going to be looking at something called the cosine law. That will give us Friday of this week and Monday of next week to review. And that means that your unit exam in trigonometry is scheduled for Tuesday of next week. You will be getting your second assignment. I mean, I can give it to you today, but you don't really know how to do it yet. I'm going to be giving you your second assignment on Thursday, and it's due Monday. And what that means is you won't get it back before you write the exam. But if you want to get it back before you write the exam, then just give it to me Friday. It's not going to take you long to do this assignment. But I don't want to give it to you now because you'll look at it and you won't know what to do at all. So what we're looking at today is applying the sine law to find information out about triangles. And the sine law, everybody, is not opposite over hypotenuse. That's not the sine law. The sine law is something different. Okay? So I want to start by talking about triangles in general. When you use Sohcahtoa or the Pythagorean theorem, you can only use those if the triangle that you're talking about applying them to has a right angle. Right? That's the trigonometry that you learned in grade 10. I'll remind you what Sohcahtoa means. Sohcahtoa is a mnemonic device, a memory device to help you remember that sine of a rotation angle is opposite over hypotenuse, so SOH. Cosine of an angle in a right triangle. Now, I believe I might have just misspoke, but I can't remember. I might have said sine of a rotation angle there. And if I did, I apologize. It's not a rotation angle we're talking about. It's an acute angle, one of the small angles in a right triangle. Sine of that angle is equal to opposite over hypotenuse in a right triangle. Cosine is equal to adjacent over hypotenuse. So there's your CAH, and tangent of an angle in a right triangle that's not the 90-degree angle is opposite over adjacent. The Pythagorean theorem, of course, you know, hypotenuse squared equals other squared plus other squared. But my point is, you can do that stuff if the triangle contains a right angle. It works. Those are right angle mathematical ideas. For triangles without a right angle, you cannot use those tools. And that's where we're going. The trigonometry we're dealing with over the next 3 days deals with triangles that do not have a right angle. If there's no right angle, there's no hypotenuse. So we can't start talking about Sohcahtoa, and we can't start talking about the Pythagorean theorem. A triangle that does not have a right triangle is called an oblique triangle. So when you see that phrase, oblique triangle, all it means is it's a triangle like that, or this, or that. It's a triangle that does not have a right angle in it. Now, I want to warn you about something. You might be given this triangle here. And I would be the first to admit that that sure looks like it contains a right angle, doesn't it? Kind of? Does that look like 90 degrees to you? Could be. But if I don't see that little box in the corner, I can't assume it's 90 degrees. It might be 91 or 89 or 90.005. But you need to see that box. So that's not a right triangle. If I showed you this, that is a right triangle. I'm just slightly curious. It's about 91. It's a little bit, I don't know if you can see it from where you are, but it's not quite 90. Not that it matters. All right, so what is the sine law? What the sine law does is relates for a particular triangle, any triangle, the length of the side that you're looking at to the sine of the angle across from that side. And I don't know if your Math 10 teachers use this notation. I really don't like, but your textbook does it, calling this BC. I don't like that. I think that's clunky. What that side is side A, and the reason it's side A is because it's the side furthest away from angle A. So we use capital letters to designate an angle or a corner or a vertex. Vertex is just what an angle or a corner is called in math. We use capital letters to denote the vertices, which is plural of vertex, and we use lowercase to denote the side lengths. And it turns out that if you draw a triangle and you measure the length of one side and you divide by the sine of the angle across from it, and then you try it for the other side and you try it for the third side, you get the same thing. And we're not going to prove this. You're just going to have to accept that it's the case. By the way, I've had students, surprisingly, I had a student one time come to me. I don't know why. Give me a second here. I'm not quite sure why that's there. I'm hoping that this is what you're looking at. Okay. I had a student come to me many years ago and say they were absolutely baffled by the sine law because they thought it meant every triangle in the universe, if you take a side over the sine of the angle, you get the same number. And that's not what this means. It means that for this triangle, A divided by sine A will give you the same as B divided by sine B, and it will give you the same as C divided by sine C. But for a different triangle, those three things will all be equal, but they'll have a different value than they do here. Are you picking up on my drift here? Okay. What this formula is actually a lot of formulas. I'll get to this in a second. This formula is actually three formulas. I can write A over sine A equals B over sine B. I can write A over sine A equals C over sine C, or I can write B over sine B equals C over sine C. I really hope, that we're all crafty enough to understand that if I give you a triangle that's labeled PQR, we don't run screaming from the room because we don't know what to do because there's no A, B's, and C's, right? What the sine law says is side over sine of angle is the same for pairs of sides and angles. Sides of angles, and angles rather. We'll get to that later. So let's dive in. Let's look at a few examples. This is not difficult stuff. You just need to be shown the procedure for doing this. Allison and Bobby leave their cabins to meet at the confectionery. Well, that's convenient. A for Allison, B for Bobby, C for confectionery. Okay. How far must each one walk and who walks further by how much? So Allison's house is 2.5 kilometers away from Bobby's cabin, and those are the angles formed by the lines connecting their houses to each other and their houses or cabins to the confectionery. So what you want to find is this distance, which you have to be pretty careful here. This distance is labeled A, isn't it? because it's across from angle A. But that distance A is not the distance Allison walks, it's the distance Bobby walks. Look at the diagram. Bobby has to walk that distance, so be very careful with your letters. And we also want to find B. Now I want to talk about something, and that's B because it's across from Bobby's cabin, and B is actually how far Allison walks. I want to talk about something in very general terms. Well, I'll make it a little specific. If we have if we have P over sine P equals Q over sine Q, just as an example of an application of the sine law, and I told you you want this, do you agree that if you want to calculate P in that equation, then you need to know capital P, lowercase q, and capital Q? Yes? You need to know everything else, all right? What if I said to you, you want to find angle Q? Well, you would need to know little p, angle P, and little q. Would you agree? My point is this. You cannot use the sine law unless you know a corresponding side and angle pair to put in there. You have to know P and P or Q and Q to use the sine law in this example. So the only way you can use the sine law here, since this is the only side you know, is if you know that angle. You need a pair. You need a side and the corresponding angle. So I would like everybody to calculate what that angle C is. And this has very little to do with trigonometry. It just has to do with triangles. I don't want to know the answer. Is that why you're putting up your hand? Yeah, I just want everybody to calculate it for now. I believe it's going to be, though, 39 degrees. 31 degrees. I'm going to change my mind. 31 degrees. And what we're doing here, and it may seem very obvious to some of you, but on a written response you would need to show this, is that those three angles, 61 degrees plus 88 degrees plus angle C, has to give us a grand total of 180 degrees because that's how triangles work. And how you sort that out in your head, whether you add those angles and take them away from 180, or whether you solve it as an official equation like I've written, doesn't matter. It's 31 degrees. Now we're off and running, and this again is the key to the sine law. You need to know a pair. You need to know a side and the corresponding angle. And I really would prefer that you avoid the word opposite. Like, you know, the side and the angle are opposite, but I always say they're across from each other. I don't want you to think there's an opposite side like Sohcahtoa has an opposite side. So now what we're going to do is we're going to pick on one of these letters. Let's find side A. We can write A over sine A equals C over sine C. I'm perfectly aware many of you do not need to write that down. Right? You can probably just dive right in and say 2.5, pardon me, A over sine 61 degrees is equal to 2.5 kilometers over sine 31 degrees. Now, again, I didn't teach any of you Math 10, so I don't know how you would have been taught to enter this in your calculator. But one thing I want to point out to you is that sine of 61 degrees is just a number, okay? That's all it is a number. If we want to know what it is, we can go sine 61, but I don't really care to do that because it's not important what the number is. It's a number. Sine of 31 degrees is a number. So fundamentally, solving this equation is no different than solving this equation. It isn't. And one thing I want to point out to you is that in this equation we're solving, whether it's the one I made up here or the one that is the question, The unknown, this is really important, I believe. The unknown, the thing we're after, is on the top. I think it makes our lives much easier if our unknown, if there's a fraction, is always on the top of the fraction. Because then all we have to do is multiply both sides by the denominator of this to solve for the numerator. And I know that what we can do is cross multiply. So let me go through this with this particular example on the right. I know that if you cross multiply, you get 17 times x equals 3 times 10. And then you would say I need to divide both sides by 17. So you would have 3 times 10 over 17. But I want you to notice that, well, cross multiplication won't always work in math, first of all, okay? It's not always going to be this simple. I want you to notice, though, that really a better approach in my mind is to say this 10 right here, that's trouble. We got to get rid of it. We want x by itself. How do I get rid of it? I multiply both sides by 10. These cancel, and I'm left with my answer. You with me on that? How many of you are taught the fish thing? Don't use it. Stop it. I mean, it has limitations. You can use it. I'm not saying don't use it. If it makes sense to you and you understand when you can use it, that's great. But we're going to encounter situations where cross multiplication or the fish thing just doesn't work. It becomes too specific. Okay. So in my mind, when I look at this, I just say, well, I want a by itself, so I'm going to take 2.5 over sine 31, and I'm going to multiply by sine 61. I'm multiplying both sides of this equation by sine of 61. And, you know, the fact of the matter is sometimes we do care only about the answer. I don't care what sine of 61 is or sine of 31 is. I care what a is. So I'm going to enter this in my calculator, 2.5 sine 61. With the TI family of calculators, anytime you hit sine or cosine or tangent, there's a bracket forced on you. And you need to close the brackets, otherwise it's going to calculate all that stuff and include it in the brackets. We don't want that. So close the brackets on that argument of 61 degrees and divide by sine of 31. You don't have to close the brackets on the 31, by the way, because that's your final operation. But I will. So this is the answer, well, not the answer. This is side A, 4.245 kilometers. Any questions on finding A? Okay, we're going to rinse and repeat here and find B, that's all. Could we use, everybody, this pair to find side B? Yes. I would not recommend it because this number that we've written is a rounded value. If you want to use that pair, you should carry all of the decimals, and if you have a way to weasel and maneuver your way around your calculator and use all the values, then do it. But I'm going to go back with the original information. So for the next one, get rid of this. I'm going to put, I'm basically now going B over sine B equals C over sine C. But again, I don't know, this line you don't really need to write. I could have just looked at the diagram and said B over sine 88 is equal to, the pair I know is 2.5 over sine 31. So I rearrange this for B by multiplying both sides. I'll show it this time. What I'm doing is this. And the effect that has is these cancel, and I'm left with B by itself. You don't need to show that. So 2.5 sine 88 over sine 31. Do me a favor and calculate that for me. $4.85. So that's A, 4.851. This is not really a difficult problem, but if you consider that it might be a multiple choice question and the question is who walks further and by how much, it can be confusing here. There's a lot of work going on, and then we have to contend with the fact that A is how far Bobby walks, right? So it was nice they kind of gave you letters that stood for things, but it was actually misleading. Allison walks 4.851 kilometers, Bobby kilograms. Bobby walks 4.245 kilometers. So who walks further? Well, Allison walks further. By how much? I guess we can subtract those two numbers and get a rough idea of how much further Allison walks. We would take that number and subtract the 4.24541. That's probably good enough. Allison walks about 605 meters more, 0.61 kilometers more. Any questions with that first example? All right. These ones are very challenging for people because they don't give you a picture of the triangle. You have to construct it yourself. So number 2 says we have triangle LMN. We have angle L given as 64 degrees, and we have side L given, which is 25.2. Now, my advice is to draw this based on the information given in the question, starting with the angle and the side that you're given, and then you might have to erase it or adjust the diagram to make it look a little better, but it doesn't really matter if your diagram is poor or not. For example, what I would do is I would just draw an angle that I believe is about 64 degrees. I don't know if that's 64 degrees or not. It's going to be pretty close. It's maybe about 67 degrees. It doesn't have to be perfect, but I don't think it's a good idea to draw an angle that's like 12 degrees and call it 64 degrees. So we can label this as angle L. And again, keep in mind I may decide to erase something. Side L is 25.2. So here's where looking forward becomes important, forward thinking. If I put my 25.2 here, and I'm going to erase that in a second, but I put 25.2 there. I say this is little l. Look at m. M is 16.5. So one of those other sides is 16.5, which is considerably smaller than 25.2. So what I might decide to do is when I put in this, I might decide to angle it slightly, so that then I can say this is M. And you don't need to get out the AutoCAD or the drafting tools, but if you're about to say that this is 25.2, then it makes sense that you can get away with saying this is 16.5. I'm not even going to use a calculator or think too hard on it. 16.5 is about 2/3 of 25, about. Very roughly. And that line looks like about 2/3 of the other line. Could I improve it by making M even smaller? Sure. But you get my drift here that you want something that looks reasonably good. Let's put in the other information that we know. We can clean up this diagram now. This is 64 degrees. Oh, well, there you go. There's our pair, right? We know a side and the angle that go together. Determine the measure of angle N. Wait a minute. If this is M, then this is capital M. What we are asked to do is find this. Is it clear that we can't find M directly right out of the gate because we don't know side M? So when I talk about P over sine P equals Q over sine Q, and I say you need to know a pair, you also need to know half of the other pair, don't you? So in this diagram, we can't find N directly because we don't know little n. But we can use the pair of L's and half of the pair of M's to find the other M and then go from there. Now, don't write anything just yet. Just look up here. If you write out the sine law the way it would be on your formula sheet, you would have 16.5 over sine, whoops, I don't want to do that yet. Yep. You would have 16.5 over sine M equals 25.2 over sine 64. Just give that some thought as to what I wrote. Side over sine of corresponding angle equals side over sine of corresponding angle. But remember what I said. I want the unknown on the top. It's easier to work mathematically if your unknown is on the top. So when I write out the sine law for this, I don't put, for example, P over sine P equals Q over sine Q. I don't do that if I'm trying to find the angle. What I do is this. And if you follow that advice, you're going to be a lot more successful in working with the sine law. What I'm doing is basically taking the sine law and flipping it upside down. So, I mean, I suppose you could write this and then go, oh, my unknown is on the bottom, let's flip it over. But you might as well just write it flipped over to begin with. So this is sine of M over 16.5 is equal to sine of 64 over 25.2. And if you look up here, we're trying to get M by itself. This is the troublemaker, the 16.5. It's in the way. So let's multiply both sides of the equation by 16.5 to get sine M equals 16.5 sine 64. I would prefer to put the number then the sine when I write it out. Over 25.2. And now I can figure out what M is, because M will be the inverse sine of that beast of a number, 16.5 sine 64 over 25.2. And I think at this level, I think you calculating all of these numbers in the brackets and stuff is not what we want to focus on. You want to focus on the algebra, which leads us to how to find our answer. That being said, you don't have to do it in one shot. You could go 16.5 sine 64 divided by 25.2 and then take the inverse sine of the answer. It's 36 degrees. So angle M is 36. Well, now it's a matter of finding this angle. and we're using again the idea that all three angles have to add up to 180. I think if you take 180 and subtract the sum of those, I believe you get 80, don't you? Those two add up to 100. So I need another 80 degrees in here. This angle is 180 minus the 64 minus the 36, which is 80 degrees. And now I don't know. It's not important. I'm just curious if I measure that angle, what kind of angle do I have here? About 83 degrees, 84 degrees. It doesn't really matter, but I find that students are better able to learn if they're looking at something that's reasonably well drawn. Any questions with number 2? All right, I think we have just one more example to go, and this deals with solving a triangle. And when you see the phrase solve a triangle, what you are asked to find are essentially everything that's missing. So in this question, you're given 2 angles and a side, which means there's another angle we don't know, and there's 2 other sides we don't know. Well, let's start by drawing it. 82.6 degrees is a pretty steep angle. We'll call that 82.6 degrees, and this is angle S. We want to draw now, this is my thinking, I want to draw side S so that I have an angle that's like 26 degrees. That it looks like 26 degrees. .9 actually. So this is side S. This becomes angle T. It's RST, so this other one must be R. And I wouldn't get too hung up on, if you have difficulty drawing a decent diagram. But again, do your best. So this is 82.6. What else do we know? R is 53. This is 53 because it's opposite angle R. That's what we know. I've always been a fan of making a list of the things you want to find. We want to find angle R, side S, and side T. By the way, very minor, but when you draw a lowercase s and you draw a capital S, they look the same, right? Make sure you draw big and small. Yep.
I think our book has t is equal, or little t is equal to 50, or at least mine does.
Your book has little t is equal to 53. So I just want to check here, Joel. You're saying this is a t on your handout?
Yep.
Everything else is the same? Okay. We're not going to change what I have up in your book. We're going to use what you have in your book. So this is 53. And I guess what we're trying to find then is not little t, but little r. Thank you so much for letting me know. Do we know a pair at this point in time? We do. Do we need a pair to find the missing angle? No, because we know 2 of the angles. Let's clear that off of our plate first, because it's going to be the easiest. Finding this angle is going to be relatively easy. We can take 82.6 plus 25.9 and take it away from 180. $81.5? 71.5. I'll warn you, I very often I have an extra 10 degrees somewhere. I don't know why with triangles. 71.5 though is right? Okay. So R is 71.5, and I'm not going to show my work here. We know that those 3 angles have to add up to give 180. I guess we can use the sine law now with the 53 and 25.9. That's a pair. So I can put 53 over sine of 25.9. A very common mistake is to forget the sine, is to just put 53 over 25.9 equals, let's find S. S over sine 82.6. And if we do the same kind of thing, we can do the same kind of thing to find R. 53 over sine 25.9 equals R over sine of R, which is 71.5 degrees. There's our work. You don't need to really show anything else. You should know that to get R by itself, you'll multiply 53 over sine 25.9 by sine 71.5. It shouldn't be that onerous of that difficult of a task. I'll give you a minute to calculate R and S. I'm getting for S 120 roughly. For R, I'm getting approximately 115. You know, that's not bad. I mean, just looking at that triangle, those two sides appear to be pretty close in size. I don't know that they're to scale with the 53. I think that should have been drawn smaller. In other words, this is probably not 26 degrees. I probably drew it like 36 or maybe even more degrees. But anyway, what was the first one I found? The first one I found was S. S is approximately, you put a dot above the equal sign to indicate approximately 120.4. And R is approximately 115.1. And there you have it. So we have two more topics to cover in this unit. The topic we're going to cover tomorrow is an extension of the sine law, and it is a very, very greasy concept that we're going to have to talk about tomorrow. And then on Thursday, we're going to deal with the cosine law. And the reason why we need another law for triangles is if I gave you this triangle and ask you to find missing sides or angles, I mean, if I gave you some wood and a protractor and meter stick, you could construct this. And the fact of the matter is, this will have a particular length, but the sine law can't find it for you because you don't know a pair. Similarly, if I gave you 3 different lengths of wood and I said put them together to form a triangle, you would have to build the triangle knowing these 3 sides. But the sine law would be unable to find any of the angles. The cosine law is what we would use for those. So I've got text page 108, 1 to 5. I've also got additional problems there, but I didn't list any. I don't know that we need to. If you can get these all done in the next 25 minutes or so, then you're a master of using the sine law. Give me a couple minutes to do a couple of quick things, and I will get your quizzes back to you. And remember, if you did not write the quiz, so that would be you, Grace, right? Who else? Oh, Kai, I already talked to you, right? And Adriel, who's not here, so just you two. So, are you going to write it after school, or you want to do it tomorrow at lunch? After school tomorrow? Yeah, we can do that. It'll only take about 10 minutes. Don't go to the exam room, though. Come here. Yeah, for sure.